this stuff, adding heat, so most likely my Mach number is going to drop. But will it drop enough before it actually hits the nozzle? Because the nozzle, I have got a supersonic flow or potentially subsonic flow. I don't know what the condition is to. But if I have a supersonic flow going through a nozzle, what happens? Velocity goes up or down? Supersonic, assuming supersonic, it's going to go down. So that's my Mach number I'm telling you is choke. So most likely I'm actually supersonic in this chamber all throughout. From Mach 2 all the way to the exit, I'm supersonic. So M2 is going to be actually supersonic because of the nozzle. Now, how do I go and determine this? Area ratio, find out Mach 2. Yes. The area ratio to find out Mach 2. Let's write the area ratio equation first. Right here. So, area of area star is equal to 1 over m multiplied by 2 gamma plus 1. 1 plus gamma minus 1 over 2 m2 gamma plus 1 over 2 gamma minus 1. So generally, you went, so this is the part that is a little bit cumbersome with the equations. If you already have your area of area star, you went inside the table and you looked up the Mach number, right? And you will find that you have area of area star for two conditions, either a supersonic condition or a subsonic condition. Now, the assumption that 2 is at supersonic condition based on one key point. When can I ever get subsonic at 2? No? So why did I make the assumption that 2 is supersonic? No? You can get subsonic. But there's only one way we can get subsonic. Shock, exactly. If you don't have a normal shock, you can't get supersonic. It's gonna be, you can't get subsonic. You're always gonna be supersonic. But in this case, I've got a supersonic inlet and I've got a sonic exit. Unless I have a normal shock in between, I do not have subsonic flow. And I didn't mention anything about shocks here. I just said frictionless or whatever, but that's the only way you're going to get subsonic at 2. If you have a shock in there. Now, we're not talking about normal shocks today yet. We're going to be reviewing it. Today's Thursday, so next week. Next week we'll go over normal shocks, but for now, assuming no shocks are inside, what can station 2 be at? Supersonic. So now that I have supersonic, you typically would go into the table, use area 2 over area 3, and you figure out the Mach number. And you will have 2 solutions, right? That's if you're using the table. How do you go and solve this? Because you have this, but you need M, and you got 2 terms. Okay, that's very good. So everybody is visualizing what your colleague mentioned? What did he say? He says use a solver. If I already know this, I could make an assumption for this and then figure out what this is and then iterate until I converge that this M and this M have to be equal. And that's my Mach number.
That doesn't sound
So use an iterated method.
That's horrible. Sounds horrible.
He's smiling.
No, you're not going to do it manually. You're not going to do it for, maybe for one homework problem I'll have you do it, but in reality, you're doing it for propulsion systems. I mean, think of it this way. What are you going to do? If you're given this problem, and the Mach number keeps changing for an engine, what are you going to do? You're going to keep looking up the tables? How did the tables work? How are the tables generated?
Equations.
It's the same, from these equations, they iterated, and they got into the tables.
On MATLAB, there's a syntax that if you put in the area ratio and you say that it's subsounding, it'll give you Mach.
There you go. So there you go. So you can do it in MATLAB.
Yeah.
But yes, essentially, and you can do it in Excel. Just simply by putting that value, guessing what that Mach number is, and then iterating until two Mach numbers actually converge, you have the Mach numbers. Now you're going to get two answers for this, right? Based on this equation, I'm going to get two answers. I'm going to get a supersonic Mach number, which I will say trial and error.
I mean, I didn't have to. I didn't for the project. I didn't do air that. What do you call it?
Let me write the equation in terms of the stations so we don't get confused first.
Oh yeah, you put in MATLAB.
Area 3 over area 2.
Find the value.
Sorry, this is the area 2 over area 3 is equal to area 2 over area star.
I mean, I don't know how to do the next one.
And based on that, I'm going to use 1 over m2
I can learn.
multiplied by 2 gamma
So I did
plus
both.
1 multiplied by 1 plus gamma minus
Same thing
1
I
over
have to
2
do for
m2 squared gamma
I'll just tweak my code.
plus 1 over 2 gamma minus 1. Okay, so using trial and error, I just written a code for it.
Okay. Okay.
And Jason just mentioned there's a solver in MATLAB that you can just do this with, or MathCAD probably has a solver if you put an equation and say, find out what that value is, that's where you're going to get. Code-based or Excel, you can do it in Excel. What you're going to get is two possible solutions. And I already did this and I got two Mach numbers. M2 is equal to 1.81 and M2 is equal to 0.45. And we just said, when can I ever get this? If I get a normal Shotkin sign. And actually there's a lot of complexities with heat addition and actually getting a normal Shotkin sign. You have to be really doing something wrong to induce that shock. But anyway, so this is not possible. This is a possible solution. No, not possible. So this is my possible solution. It's a supersonic flow. And as I said, it's essentially what you would do if you're doing the tables. You will take area 2 over area star, and you will look for area 2 over area star, and you'll find two answers for the Mach numbers. But think of this as an engine. If there's a compressor or an inlet duct for a scramjet, because this is primarily a scramjet, if there's an area inlet duct, if you're changing your flat Mach number, that's going to change your M2. And if you change your M2, it changes quite a bit of what happens downstream as well. So every time you're going to be iterating quite a bit on the conditions that keep changing throughout. Because then you might not be choking that nozzle. So think of it this way. What if this nozzle is actually still at supersonic at 1.2? Then you're going to be changing your air ratio. You're going to create that virtual nozzle that goes to choking condition and go back and figure out what the Mach numbers for that nozzle that it's selecting cut off. So if I go and cut this nozzle right here, right, and I'm telling you station 3 is now right here, so the Mach number there is going to be at a higher Mach number than 1. You've got had a question.
Yes. So you said it's not possible for the subsonic because there's, you assume there's no shocks?
Yes.
Okay.
Right here. Where's our curve? How are you going to get from supersonic to subsonic? There's two ways, right? I could just go around the loop this way, or I could just do this. When can I ever do this? Shock. So I need to go from supersonic to subsonic. I could just follow the path, or I could actually just have a shock, a normal shock inside. Or a strong oblique shock. We're going to go over shocks, but why are we wasting time with shocks right now? We're going to do it next week. If you want to get ready for the midterm, I'm trying not to include shocks. But let's not talk about shocks right now. I'm assuming no shocks right now. It's not possible to get subsonic in this flow without a shock. So therefore, this is supersonic at 2. This is the answer that I got for based on my iterative method. What do I do next? I'm trying to find out Q. How did that Mach number help me? What? What do I do? This is supposed to be review folks. This is not supposed to be new material. Find T2. How do I find T2? So I've got T2. How do I get T2? I have the Mach number. Do I have anything else? Got T1. Okay, so T1 over T2 over T1. If I pull up my equation, what do I have? What do I have? So the colleague's mentioning, let's use this equation, which is equal to M2 over M1, 2, 1 plus gamma M1 squared over 1 plus gamma M2 squared to the power of 2. Do I have my Mach numbers? I have Mach number at 1, and I have my Mach number at 2, so I can get T2 over T1. Okay, so let's say I got my T2 and my T2 multiplied by T naught. Essentially, what are we trying to find out? We're trying to find out Q in, so instead of confusing ourselves, is equal to T stagnation 2 minus T stagnation 1. Now, do I know how to get T stagnation 1? Yes. T stagnation 1 is equal to T1 over, T stagnation 1 over 1 is equal to 1 plus gamma minus 1 over 2 M1 squared. Now, I already know my Mach number here, and I know my static temperature right here, so I could say, well, from this, T stagnation 1 is equal to 170 Kelvin, 1 plus your 0.4 over 2 Mach number squared, and from that, T stagnation 1 is 306 Kelvin. Okay, so now that I have my T stagnation 1, I need my T stagnation 2. And T stagnation 2, I can simply say, well, T stagnation 2 over T stagnation 1 is equal to T stagnation 2 over T2 multiplied by T2 over T1. And I already have my T1, so I can just simply use the same equation, or I can just say, I'm going to use the same exact equation, T1 over T stagnation 1. I'm going to pull up the same exact equation that we've written for the last example problem right here, and say, well, T stagnation 2 over 1 plus gamma minus 1 over 2 m2 squared over 1 plus gamma minus 1 over 2 m1 squared multiplied by m2 over m1 squared and 1 plus gamma m1 squared over 1 plus gamma m2 squared to the power of 2. So all I did was just write the same exact equation that we used before, and you could just use it as a rule of thumb for Rayleigh flow anyway. So now that you have this, I already know my T stagnation 1.